First, thanks, Stephanie, for the kind introduction. And I have to admit, when Rebecca approached me for giving a talk, I said, really, me? I'm a photonic guy. Then he said, this is a challenge. I said, okay, this is my effort, first attempt, try to answer the challenge, to look at the nanotechnology in the lens of radiotheranostics. So, disclosure, we finally have a company. And everything we have done so far is not funded by the company, is purely academic. I just want to mention that. So porphysome by name is porphyrin. And porphyrin is a color of life. It's actually make your blood red, make the grass green. It also perform all the function in terms of making our life exist. But because of this the property of the photonic property, is very well known as photofluorescence imaging contrast agent, very known as a photodynamic therapy agent. But about 13 years ago, we actually converted by radioisotope using copper-64 to replacing the magnesium in the chlorophyll or the iron in the hemoglobin with copper-64. Now we transform a photonic material into nuclear massive materials. And that was actually very cool. Initially, we thought that was a nice discovery, but look at literature, it is not. The copper-64 into the porphyrin was known in 1951 in the Science paper. In 1957, 27 patients in Mount Sinai, New York, got injected with copper-64 porphyrin. That was way before a lot of PET everything started. So we basically find it out later. The porphyrin is a theranostic material, probably more broader than the traditional radiotheranostics per se. So one of the examples we did is when a collaboration with Ben Neal many years ago, about 11 years ago, we actually using the intraperitoneal injection of a folate targeted porphyrin with a peptide as a pharmacomodulator linker. We're actually getting very nice image of the metastatic, essentially all the ascites lighting up versus the control, and we actually demonstrate the metastasis overall average metastasis with background is about 3-to-1 ratio. So that was actually pretty cool. Then we were talking about, how about nanoparticles, right? When you think about porphyrin as theranostic, what about nanoparticles? So this is actually the work we have done now is 13 years. Essentially, we actually find out when the porphyrin conjugate to a lipid, it behaves as a lipid. What lipid do? Lipid form liposomal structures. When the porphyrin lipid do, they form a liposomal-like structures. And so that's what the name of porphysome does, right? Porphyrin, liposome, and Google it, nobody use it, so that's the name, right? But the importance of this discovery of this nanoparticle is multiple-fold. First, you think about it. There's more than 80,000 of this molecule self-assemble. Each molecule is about 1,000 molecule weight. When they self-assemble, what happens? Well, you absorb a lot of heat. All the light absorbed, everything not giving up by fluorescence because everything's quenched. There's so much dye was absorbing. What happens is like a black hole. What the black hole does, it becomes very nice as a photothermal conversion agent. So we demonstrate you can do the photoacoustic imaging agent, you can do the photothermal therapy agent. But when it's actually porphysome like a liposome, they disrupted, the fluorescence property and the photodynamic therapy property get restored. So now you can do activatable, very low background fluorescence imaging and do the photodynamic therapy. Now that's getting exciting because we know the porphyrin can radiolabel. What if the nanoparticle per se? We actually can demonstrate the entire nanoparticle can be directly radiolabeled, very highly labeling here, and then we actually show trace amount labeling can give very nice PET imaging agent. So now porphysomes becomes useful in tracking what happened to the nanoparticle behavior in vivo. Another important thing is because we have 80,000 porphyrin, each one of them can label metal. What if I label so many paramagnetic metal like manganese? Now you can, in the potential to address challenge of MI sensitivity, because simply we have 80,000 MI contrast agent. Recently, we also demonstrate we can get a copper-67 labeled to do a SPECT imaging. Obviously, we're thinking about radiotherapy per se. And another interesting angle we actually observed is by directly activating by the porphysome without metal, with about 6 MV LINAC radiator, we can have an anti-tumor effect. that is another angle we are very interested. Both of the radiation and the so-called radiodynamic angle is we hope to bring them to beyond light. Finally, another interesting angle we observed recently is the porphysome generating under light treatment generate tremendous of immune response. And that immune response is with such a low light dose, we don't deplete any immune populations. Innate, adaptive, everything pops up. And we actually demonstrate you can use this to treating the metastasis tumors that in a way is taking the nanotechnology designed originally for photonics beyond local, right? So that's the idea. So the whole purpose of so far is basically tell you porphysome nanoparticle is an intrinsic radiotheranostics. Now, the first radiopharmaceuticals we made from this is copper-64. That was in the 2012. We have this paper published. Actually, in that time, this is the first example of in organic nanoparticle can be intrinsically labeled without adding a DTPA or the chelator to preload them, then liposome, then try to label them. So essentially what we have is what we get. Once we have that, we got a very high labeling efficiency, and we can see the series dilution, all the same maintained. This is probably one important. Essentially 30 hours post-IV injection, the chemical integrity would remain. So the copper-64 stay with porphyrin and they stay intact. And this is actually the challenge which David Jeffrey was talking to me about. He said, how much you can label? I said, why you need to label so much copper-64? He said, just try. So this is what we tried. Because there's 80,000 porphyrin, and we can label up to 2,800 curies per nanoparticle. I don't know how to use them for, but that time it's just fun to have, right? So the next what we do is we think about it. Because the copper-64 is a tracer, and we really want to design this initially, the whole purpose is photonic materials. So we want to consider, is a copper-64 really representing the porphysome as a radio tracer? Indeed, we show the structure properties exactly maintained, the copper-64 porphysome versus the porphysome. We show the biodistribution is maintained from 6 hours to 30 hours, everything equal. So that means whatever we do copper-64 porphysome indeed will representing the actual porphysome behaviors. Then what we do, we want to see, is that selective, right? We actually tried to so many different models from different species. If example here, you can also topic models from mouse to rat, to rabbit, to dog. You should cross the street, the tumor selectivity was maintained. The next step, we actually did so many different models. For example, this is the metastasis, bone metastasis, and this is abdominal metastasis in the ovarian, in endometrial cancer. This is the metastasis to the ovary. You can see the two ovary, we show very nice PET scan, and these were confirmed by the fluorescence, by the bioluminescence, and also by the histology. And we also show this is oral. So in essence, we have done so many different models, different species, different cancer type. Across the board, we observe very high tumor selectivities. Then the next step is the most important for the tracer, is allow us to do quantitation of the nanoparticle, distribution, selectivity, pharmacokinetics. That is critical because that is eventually very useful for the treatment planning as a dosimetry tools. Most recently, this was fresh out of the press, essentially my student and the Bo Wang's group in the AI scientist at the UHN, we have figured out a way to using, basically we're creating the deep learning model called nanomask that can validate in a preclinical for copper-64 porphysome PET imaging that allow us to do the dosimetry, give the pharmacokinetic output. Most of AI can beautifully do the machine learning, showing the auto segmentation, showing the imaging analysis very nicely. But we did a step further. We demonstrate with a few scans, not even entire organ system, we actually can predict the pharmacokinetics output of the entire system. If this one works well in the future, potentially in the clinically, we could consider a few PET imaging scans will allow us to do more of these dosimetry measures. Now, with that in hand, knowledge in hand, we actually designed the clinical trial that is led by Stephanie, my friend here, and she and Amy Oza's group did a really nice way to design based on the porphysome's intrinsic properties, inherent multifunctional property, design this experiment. This is actually protocol called phase 1A, 1B design, essentially using the phase 1A first to do the first inpatient, and then use the PET scan for the advanced ovarian cancer patient. And the dose we obtained in the phase 1A will be actually determine inform the starting dose in the phase 1B, which is also will be safety study, but in a therapeutic context, right? Because once we start a very low dose, then we're actually escalating the cold dose without changing the radioactivity. They will allow us to predict actually gaining the dose to do the treatment values. So far what we got the Porphysome GMP done in the BC cancer, very good clinical collaboration. They have a very good liposomal cancer production there. And this is actually, this is the copper-64 Porphysome GMP production, really thanks to my partner at Ray Riley, I think he's here somewhere in the pharmacy. And this is how close we are. The copper-64 will be labeled here, and about 200 meters away, 15th floor, 18th floor, I think that will be the radio infusion facility, and we're planning to do the treatment. And the idea so far is for the 200 micro patient dose per week, and this is QSAR is done, investigator brochure is done, and now we are in the final process for the CTA application. Finally, I can say I no longer will be acquiring wolf. I will say finally I get into Porphysome into patient very soon. So in terms of phase 1B, as I said, I designed this, originally designed as a photonic material. We're still going that way. Because this is example we're trying to do. In the head and neck cancer with my colleagues, John Irish here, essentially designed, we actually think about the close margin resection of the oral tumor. You tweak out the tumor, and you want to use the light to clean up surgical bed, is for the cleaning. And this one, we actually, preclinically, we got a very high disease-free survival at a 25 joule per centimeter square, very, very low dose. And we actually taken it further to the veterinary patient in Guelph. This is the melanoma in the tongue of the dog. I don't know why the melanoma go to the dog or tongue, but this is the melanoma tongue dog, and you can see the tumor clearly, but you can see all these other small lesions is important to creating this visualization is important. This is in the cat or tongue tumors. The cat is ready to be euthanized because the tongue sticking out couldn't even retract. It's too big. After our treatment, you can see the cat is now completely, quality life regained. They can eat, they can drink, and once we do that, then we're actually taking this cat back for the curative treatment, the next step. We have done about many of these, about 10 or 12 dogs and about 10 or 12 cat patients so far. Another angle we want to do is lung therapy. And for lung, we're actually introducing for the transbronchial way, try to do the very minimal invasive way to the transbronchial therapy, using the bronchoscope, especially try to take advantage of the robotic bronchoscope development to deliver the light directly to the tumor with much minimal invasive way. And this is we show in this rabbit model, we actually have this 1 millimeter, less than 1 millimeter diameter of the fibroscope. We can observe the lung tumor behind the wall of the bronchiole. And this is showing the human lung. We have such a wonderful UHN transplant group. We have access to the human lung. And this is how the human lung looks like. I don't know how many of you have seen this, but this is really remarkable. I mean, have access to this is really remarkable. And back to radiotheranostics. We talk about copper-64 all the time, but we always remember the copper-64 is isosteric to copper-67. And copper-67 is a remarkable radioisotope, which is a very good beta emitter, and it has a 2.5 days, I think is a longer half-life than a shorter half-life in the lutetium. So you can give multiple times. But where the copper-67 coming from, right? I never get started this work until I heard the Canadian Radioisotope Center in Saskatchewan, they started producing copper-67. We probably the very first customer got this last December. We got the copper-67. Because of the isosteric, we can transfer the entire labeling optimized protocol from copper-64 to copper-67, very high labeling efficiency. And we demonstrate you can do the copper-67 PET SPECT imaging is all as clear as the PET scan. I was very excited about it when I see this. And you can see the oral radiographic because the gamma photon. So the copper-67 works very well. The next step, we want to see, take David Jeffries' challenge, I put in copper-67, because now we're not talking about the copper-64 anymore. This, we actually can label up to 15.9 kilocurie per micromolar. I would say this is like 5,000-fold more specific activity than you can generate with Lutathera. So how to use that, that's a different question, but we can get a very hot therapeutic radioisotope carrying nanoparticle. And this is based on our original idea using IP injection for the peritoneal metastasis, and we want to use in this way to actually treating the peritoneal metastasis after our phase 1A trial in the copper-64 in advanced ovarian cancer patient. We hope to take that all the way to patient with therapeutics. And in fact, Michael, my student, actually pitched this idea, and they won the pitch competition in the medicine by design. Everything's rosy. 29 therapeutic because copper is the atomic number 29, right? The problem is, here's the caveat. The great news we got in December, the first batch of copper-67 gave us such a beautiful, I can dreaming of that. The bad news is we haven't got a second batch. There's no more copper-67, so I'm waiting for my second shipment. So again, the challenge of radioisotope production is paramountly important. So I really love to come here because now I have access to a lot of production people. So I think it's important. So if you have copper-64, please tell my student Michael. So to expand a little bit more, we talk about porphyrin has very nice 4 nitrogen as a chelator for diatom metal, like copper-64, copper-67. But they're not very good for the bigger atom because the pocket size is not big enough for them, right? So this is we actually did so much work, try to using the different way to different size, different shape, different composition, the entire slew of the nanoparticle we developed from here. But this is what I want to say. Porphyrin is very bad for big atom. For example, the lanthanide, a lot of people trying to put the lanthanide in the porphyrin, well, it ends up sits on the top of the plane. It doesn't go inside. That's why people try to develop all the way to stabilizing this, right? A lot of chemistry effort go into this. I thought, why do you go in such an extent? Why not make a porphyrin bigger? In fact, there is a porphyrin is bigger, is out there, invented by Jonathan Sessler. People in Texas, everything's big. So he named texaphyrin, right? This is the last time, I will emphasize, this is the last time a porphyrin molecule can be named by somebody without IUPAC approval. So this is, after this practice, no more porphyrin names afterwards. But he called Lone Star, right? It's 5 coordination. But really the important is, number 1 is 5 coordination. Number 2, this is 20% larger pocket. That means you can really put a lot of metal, different metal in. This is what we did. We're making a texaphyrin version of nanoparticle, and this is the metal we were able to put in 1-to-1 stable chelation. If you don't mind, I want to say, I want to actually name them: Samonian, European, Galenian, Terbian, I don't know how to DY, Homonian, Urbian, essentially you got the picture, right? And this is what we actually are interested, because now in terms of radiotheranostics, it really get me thinking, what can I do with this texaphyrin? Well, I can do lead, bismuth, yttrium, lutetium, terbium, indium-111, thallium. So these are just a few we can try to do, right? And this want to show one slide to demonstrate examples where we're working with the texaphyrin. We got, number 1, we figured a way to customize label the metal. So essentially, you can titrate the metal. We confirm the metal can be chelated in the very quantitative way, in the very exact ratio. For example, I can label with the indium, with the manganese, and in the precise ratio. Second, because there's radioactivity involved, so we actually design our own microfluidic chambers. Essentially, instead of creating all the thing, I just have a lab break, having a microfluidic chips, plus 2 cylinder pump. You can get a radio label, you can throw it away afterwards, you can actually make a nanoparticle right there using these chips. Second, we demonstrate, for example, this is indium-111 texaphyrin, which is a good OJ, but we did only the SPECT imaging. This is a lutetium-177 lutetium texaphyrin. We did a SPECT imaging of that. And obviously, the co-lutetium is very good for photodynamic therapy. And this is a gadolinium texaphyrin for the MI. So essentially, we have unlimited way to creating all these metals. The problem is, I'm always said, why we couldn't do actinium? Yes, I couldn't. Actinium doesn't go in. But lead-212, bismuth-213 is not bad, right? But I don't have access to. So I really am very happy to hear a lot of production. So you are my best friend, new best friend on that. So one final point I want to mention is beyond these radioisotopes, the texaphyrin, gadolinium texaphyrin in particular, was known as the radiopharmaceuticals. Where I'm going, sorry, going forward. Gad texaphyrin was actually introduced into the patient as a radiation sensitizer. 500 patients in North America, 500 patients in Europe, randomized phase 3 trial, and they got FDA disapproval. It's the worst of the worst. Why? Because they couldn't beat the standard radiation therapy. But to me, it's like gold mine. Why? Number one, you don't get 1,000 patients without showing they're safe. The chromophore is safe. Number two, maybe the nanoparticle is a solution. If it's one molecule is not enough, maybe 100,000 maybe is better. So that's what we want to do. Another thing is we want to see if the oxygen can help. So this is what we did with one of my old students go to Peking University. He actually said, I want to put oxygen into nanotexaphyrins. And he put a microbeam in it. I said, why? But he said, just for the fun of it, right? Science, right? So let's go for it. So what he did is actually interesting because once you have that, we can see a very strong hypoxic relief in vivo with this microbeam containing nanotexaphyrin. They don't even need a preload oxygen because the microbeam will pick up oxygen in the pulmonary system and they will pick oxygen and they will relieve the oxygen pressure. And once you have that, we can see a very good chorogenic survival. We can see the radiation actually sensitization. The Gad texaphyrin itself, nanotexaphyrin itself, has radiation sensitization ability, but added the microbeam showing much stronger. This is showing the radiosensitization effect which is beating this additive marker, so this synergistic. We compare with the nitronimazole, we actually can see the clinically used radiation sensitizer. I believe in Denmark, we can beat them on that. So this is actually exciting, even though the oxygen delivery is not the best way. So we have a new way to do that. I think that's it. And I want to just give a quick summary. I hope I introduce you Porphysome as inherently multifunctional radiotheranostics, probably in much broader sense in a classic radiotheranostics, because you can integrate in surgery, fluorescence, you can integrate in the radiation therapy, immune therapy, everything into this one. We show the radionuclide chelation of porphyrin-lipid building blocks, really converting the porphysome into radiotheranostics. I also show the next generation porphysome. I want to show one example here. We did all this microbubble and ultrasound, all the things. But the nanotexaphyrin really expand, I hope, a radiotheranostics landscape. Even though we are very, very early, I'm a beginner to learn how to do radiotherapy. But everything so far, I have to say thanks, Rebecca, to push me to think the Porphysome nanotechnology, think in the radiotheranostics lens. So thanks for that. And obviously, thanks all my students and my colleagues, particularly my wonderful 18 clinical collaborators, partners, Stephanie, John, Brian Wilson, Ray, and Kaz, and all the grants support. And I want to thank big support from the OICR as well, along with Terry Fox. So thank you, and happy to answer questions.
Thank you so much. What a tour de force of overview, and really a great example of how radiotheranostics can actually help nanoparticle and drug development. So I think it was a great example. Open to any question before actually we have for lunch, and then Gang will go to everybody for the production. I actually have one question. We often use radiotheranostics to actually look at distribution or to look at the tumor distribution as well. Why porphysome is actually so specific to the tumor?
That's $1 million question. And I think the open hypothesis is porphysome is a porphyrin-lipid self-assembled into liposome. So it has a liposomal kind of property with whether you call it EPR or call it active delivery, there is some accumulation of the nanoparticle in the tumor. But in essence, it's a single molecule. The porphyrin-lipid molecule has a very nice membrane binding affinity. It actually will help you to get into the tumor cells once in the tumor because kind of enrichment in the tumor site with so much porphyrin. And the porphyrin-lipid is taking the step further for the delivery for intracellular. So that's my open hypothesis. There is also hypothesis about phospholipase activation. There's many different hypotheses, but I think that my current hypothesis is it is simply because it's a porphyrin and it's also a nanoparticle.
Thank you.
Yeah,
Gong, thanks. A similar question. Like what's next for this technology? Is there a way of linking in nanobodies or other targeting moieties onto the porphyrosome?
It's a great question.
And then can you give us a little bit of idea of the half-life of this molecule, and do we need to do things to increase half-life?
Okay.
And what are the challenges there?
So first of all, the half-life in mice is about 12 hours, 13 hours. In the when you I think Michael is here somewhere. When you extrapolate to the patient and he has calculated the dose and the half-life, I think is like 48 hours to 72 hours half-life in human. I think that will be my. In terms of delivery targeting, we actually put in folate targeted on it. We put a PSMA targeted together with multi-pumper. And we also worked with EGFR antibody targeting. So a number of them we were able to show the targeting. But the nanofield per se doesn't believe the targeting will improve the nanoparticle distribution in the tumor. They will improve the selectivity to the tumor cells. But it's like a two-stage process, right? So we cannot avoid liver spring. That's why I'm hoping when we're pushing for the radiotheranostics, for the radiotherapy side, we try to do IEP, try to do ovarian cancer. That's why Stephanie is my best partner on that. Thank you.
Any other question? I have actually another question because we talk a lot this morning about the importance of clinical translation. What was the main barrier that you got?
I think the first barrier I would say, it's hard to deal with a device-drug combo. Whether you're from regulatory standpoint, from development standpoint, that is hugely difficult. There's a lot of lack of expertise on that. And that's why I was so amazed my friend David Kirsch would be the first person ever to put a device and drug combo approved by FDA early this year. So, I'm the only one who most will appreciate that effort. But he took about 15 years to do that, right? So second translation barrier, I would say is because of when you do the theranostic, you can do so many multifunction, that make the decision making to which to go forward is hugely challenging. Like GE come to me say, hey, I want to MRI. The Baxter say, I want to radiation therapy. I went to a billionaire in California, I don't want to name names. He asked me to go there to meet him. He said, can you do immune drug delivery? It's like what I'm going to do. As academically, it's creating great paper, but it's not creating a great development path. So that's the challenge, I would say, the two biggest challenge. Yeah.
So my question's about supply. You mentioned you got copper-67 from Saskatoon, and it was wonderful, but now you don't have any more. Is more coming, or what's the barriers that you're facing in getting the supply?
I think it's not a stable supply, not even. Sometimes the supply came like a first pilot, then they decide they don't have enough market, then they stop producing it. The government support certainly helps a lot on that. And the copper-67 also, there is a lot of supply we observe. A lot of U.S. production facility doesn't have export license to Canada. Freddie just told me he got copper-67 from Idaho. Then I check, Idaho doesn't have export license. There's so much hurdles you want to go. And that's not for me as a scientist try to address. I think that's the beauty of this forum. I think if all together, it will be tremendous. Yeah, thank you.
Thank you very much. I have a kind of a simple question. Do you usually use imaging to stratify how you go about developing more compounds? And why don't you first go into patients with imaging?
Well, you nailed it. Our first in human later this year will be copper 64 PET imaging. It will be first in human, but the only reason why we're doing so slowly is not beyond that barrier mentioned, is also we don't have industry uptake. Everything was done by research grant, dollar by dollar. Yeah, it's hard. Thank you.
Thank you so much for a great session. Really thank you, and looking forward to see the next step of the Porphysome in clinical trial. So thank you so much, everyone, and enjoy your lunch.
Enjoy the lunch. Thank you.
All right, it is lunchtime. Lunch is served in the concourse. Just feel free to eat wherever you want. There is some access to outside if you want to take in the rest of the day. But I wanted to thank our lunch sponsor, Adam V. Please enjoy, and I will see everyone at 1:30 for the beginning of our afternoon session.